You're pushing hard, and then nothing. Your legs turn to lead, a thick fog rolls over your brain, and your body simply shuts down. You've hit the wall. This crash is a hard physiological limit. Your body has completely drained its backup fuel reserve, a molecule called glycogen. Glycogen is simply stored glucose. When you eat carbohydrates, your body packs away the excess sugar as tightly bundled energy, ready for immediate, high-intensity use. We keep this backup fuel in two main storage tanks. The liver acts as the dedicated reserve for your brain, while the larger distributed network of your skeletal muscles fuels physical movement. Think of glycogen as your biological checking account. The exact balance in these two tanks dictates exactly how far and how fast you can push before you experience catastrophic metabolic failure. Let's look at what happens when we intentionally starve this system by cutting out dietary carbohydrates entirely for 48 hours. The drain begins immediately in the liver. Even when you are completely at rest, the human brain relentlessly consumes 4 to 5 grams of glucose every single hour. This chart tracks the resulting drop in liver glycogen volume. Without incoming food, the line plummets on a steep downward curve, hitting absolute zero right between the 18 and 24-hour mark. To keep your brain alive, the body triggers an extreme biological protocol called gluconeogenesis. It starts manufacturing brand new emergency sugar out of non-carbohydrate sources, like fat and amino acids. But your muscle tanks are still holding out. To drain those, you introduce an intense, heavy workout while in this carb-depleted state, forcing the muscle glycogen down to near absolute zero. At this point, the subject is a fully depleted, biochemically desperate entity. The muscles have been transformed into empty biological sponges, primed for a massive reload. So, how does the body handle a sudden influx of carbohydrates when the entire system is starved? Under normal conditions, biological rules dictate that the body needs the hormone insulin to bind with cell receptors and signal the membranes to allow glucose inside. But immediately following an intense, depleting workout, the body activates a temporary metabolic override known as the insulin-independent window. For 30 to 60 minutes, transport mechanisms rush to the cell's boundary. These vector doors act independently, catching floating glucose molecules and pulling them inside without needing an insulin signal. Because of this override, the muscles vacuum up glucose at an extreme rate. By intentionally starving the muscles and perfectly timing our nutrient intake, we bypass the body's natural speed limit, forcing the system to ingest fuel faster than is normally biologically possible. Zooming out from the microscopic level, we have to determine exactly how much food is required to complete this biological recharge over a 24 to 48-hour period. As this equation shows, a depleted body requires 10 grams of carbohydrates for every 1 kilogram of total body weight to reach capacity. Apply this to an average 70-kilogram person, and the math dictates a requirement of exactly 700 grams of carbohydrates. These 700 grams represent an immense, calculated payload of dense starches, a towering volume of rice, potatoes, and bread required for a full replenishment. To optimize this payload, you pair those carbs with protein in a 3-to-1 or 4-to-1 ratio. This accelerates the structural repair of the muscle tissue while the fuel reload is happening. Achieving maximum glycogen capacity doesn't happen by accident. It is a highly precise mathematical engineering project. This level of intake leads to a psychological shock the morning after a massive refeed. You step on the scale and see a severe spike in your body weight. This happens because glycogen is highly hydrophilic, or water-loving. Storing it comes with an osmotic cost. For every gram of glycogen packed into a muscle cell, it forcefully drags 3 grams of water inside, locking into a rigid 4-part structure. Run the final math. Storing 500 grams of glycogen simultaneously traps 1,500 grams of water within the muscle tissue. In the real world, this math translates to an overnight, sudden scale jump of a full 2 kilograms, or about 4.5 pounds. The scale has captured highly pressurized biological rocket fuel and water inflating the muscle fibers, tangible evidence that the cellular engineering protocol worked.